Hey, tonight we talk about a planet that doesn't play by the rules. Uranus sits out there at the edge of our solar system, tilted sideways, radiating almost no heat, surrounded by dark rings we still don't understand, and orbited by moons named after Shakespeare characters instead of mythological gods. This is a place where nothing works the way it should, where seasons last 21 years, where winds blow backwards, where a single spacecraft visit from 1986 is still teaching us more than 4 decades later. Before we go further, like the video if you care about weird planets, and subscribe if you want more stories about the cosmic oddities hiding in plain sight. Let me know in the comments where you're tuning in from. Now, settle in, because Uranus is a mystery wrapped in darkness, and we're about to explore exactly why this ice giant refuses to follow the script. Let's start with how we even found this place. For thousands of years, Saturn was it. That was the edge of the known solar system as far as anybody with a telescope could see. The ancient astronomers knew about Saturn. It was visible to the naked eye. It was a wanderer, a planet, one of the classical 7 planets that moved against the background of stars. But beyond Saturn, there was nothing. Nothing that anyone had documented. Nothing that anyone could identify as a world. Just empty space. Then on March 13th, 1781, an astronomer named William Herschel was systematically surveying the night sky from his observatory, not looking for anything in particular, just doing the methodical work of stargazing with a telescope. He was cataloguing stellar positions, recording observations, performing the careful work of astronomy. He spotted something, a point of light that looked odd. At first he thought maybe it was a comet or a star, something ordinary that he could catalogue and move on. But it didn't behave like a star should. It didn't move the way stars move relative to one another. Stars are distant. They don't appear to change position noticeably when you're on Earth. But this object had apparent motion. It had a disk to it when he looked closely. It was a disk. It wasn't a point. It wasn't a star. This changed everything instantly. The solar system suddenly got bigger. There were worlds beyond Saturn. There were worlds beyond what anybody had imagined or theorized. The implications were staggering. For millennia, Uranus had been visible in the night sky, but it was so faint, so distant, so visually indistinguishable from background stars that nobody had recognized it as a planet, rather than just another dim star among countless dim stars. Herschel's discovery proved that the solar system extended far beyond what previous generations of astronomers had believed. There was more out there. There were more worlds. There was more to explore. Herschel wanted to name his discovery Georgium Sidus, after King George III of England, which would have been hilarious in retrospect and completely impractical in terms of long-term astronomy. Can you imagine naming major solar system bodies after individual monarchs? That system would collapse within decades as kingdoms rose and fell. Fortunately, the scientific community didn't accept that name. Johann Bode, a German astronomer, suggested the name Uranus instead, after the Greek god of the sky. And that name made sense for multiple reasons. It fit with the classical mythology theme that governed planetary nomenclature. It wasn't a king's name. It wasn't politically charged, and it felt appropriately cosmic and ancient for a world so far from the sun that sunlight takes 2 hours and 40 minutes just to reach it. The name Uranus positioned this new planet within the classical framework, linking it to ancient knowledge even as it expanded what was known about the solar system. This discovery was enormous for science. It wasn't just finding a new planet. It was proof that the solar system was larger, stranger, and more complicated than anyone had previously documented. It was concrete evidence that human understanding of the cosmos was incomplete. The age of telescopic astronomy was beginning to reveal secrets that had been hidden for the entire history of human civilization up to that point. And the discovery of Uranus was just the beginning. The solar system held more mysteries than anyone had suspected. The thing about Uranus is that it's genuinely massive, even though it's so hard to see from Earth. It's the 7th planet from the Sun and the 3rd largest planet in our entire solar system, beaten only by Jupiter and Saturn. If you try to visualize the size difference between Earth and Uranus, imagine taking our planet and making it 4 times wider. That's the scale difference, 4 times the diameter. About 63 Earths could fit inside Uranus. If you wanted to use a really accessible analogy, if Earth was a nickel, Uranus would be about the size of a softball. It's not a small difference. It's genuinely enormous. Uranus is roughly 14.5 times more massive than Earth, which means it's not small. It's not hiding because it's tiny. It's not some distant speck that escaped notice because it's barely there. It's hiding because it's so incredibly far away. The distance is almost incomprehensible from an everyday perspective. From Earth, Uranus sits about 1.8 billion miles out, which is 19 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, roughly 93 million miles. So Uranus is 19 times that distance. Imagine standing in one place and trying to see something that's 19 times farther away than the distance from Earth to the Sun. That distance means Uranus receives almost no direct solar radiation compared to planets closer in. It's dark. It's cold. And from an observational perspective, it's frustratingly dim, even when you know exactly where to look and how to look for it. This immense distance also means that for the ancient astronomers, even with the naked eye, Uranus could never have been properly identified as a planet, rather than just another star among countless stars filling the night sky. It's too faint. Brightness matters when you're trying to see something at night from the surface of Earth. The visual difference between Uranus and a background star is essentially undetectable without magnification. This is why it took until 1781 and the invention of telescopes good enough to see planetary disks before anyone could confirm what Herschel had found. The planet exists at the limit of what ancient technology could resolve. Ancient astronomers could see the 5 inner planets with the naked eye, the ones visible to human vision without aid. But Uranus is beyond that threshold. It's beyond what the naked eye can definitively identify as a planet. This is also why learning about Uranus remains so difficult for so long. You can't just look up and study a planet that you can barely see. You need instruments. You need telescopes. You need technology that was simply unavailable for most of human history. But here's what makes Uranus truly strange. It rotates sideways, not tilted like Mars, which has a tilt of about 25 degrees that's actually similar to Earth's axial tilt, not at a reasonable angle like Saturn, which is tilted at about 27 degrees. Uranus is sideways. The equator of Uranus is nearly at a right angle to its orbit, with an axial tilt of 97.77 degrees. If you drew a line through the north and south poles of Uranus and extended it into space, that line would be nearly parallel to the plane of its orbit. The planet doesn't stand up, it lies down. This is not normal. Every other planet in our solar system spins like tops, rotating on axes that roughly align with the plane of their orbit. They're all standing up, more or less, spinning vertically. Uranus is the cosmic exception. It rolls along like a ball, tumbling through space. It tumbles end over end as it orbits the Sun. If you could watch Uranus from above the solar system, from some point in space looking down at the planets in their orbits, you'd see all the other planets spinning their usual way, and then you'd see Uranus rolling sideways like someone kicked it and it never recovered. Scientists think that during the early formation of the solar system, about 4.6 billion years ago, something catastrophic happened to Uranus. An Earth-sized protoplanet, a proto-world made of rock and ice, maybe even with its own gravitational field and early moons, collided with Uranus with an amount of force that's almost impossible to conceptualize. The impact was violent. It wasn't a gentle collision. It was a cosmic collision of the most extreme kind. A planet-sized impact. The force was sufficient to knock Uranus completely over, to flip its axis of rotation by nearly 90 degrees. The impact was so violent that it fundamentally rewrote the planet's orientation. And here's the incredible thing. Instead of slowly recovering to a normal spin over billions of years, the way you might expect a tumbling object to eventually stabilize, Uranus has maintained this sideways rotation for billions of years. The planet has been lying on its side for the entire history of the solar system since that collision. It hasn't corrected itself. It hasn't gradually returned to a more normal orientation. It stayed tilted. This makes Uranus fundamentally different from all other planets in ways that go far beyond just appearance. It's not just tilted, it's inverted. It's the cosmic equivalent of someone doing a complete somersault and then deciding to stay in that position. And that simple geometric fact has consequences that ripple through everything about how the planet works, how its atmosphere behaves, how its climate operates, and how its entire system of moons and rings functions. The sideways orientation means that Uranus doesn't rotate the way you'd expect a planet to rotate. It doesn't spin like a normal planet should. If you think about how Earth spins, you can imagine a line running through the North and South poles, and the planet spins around that line. Everything is orderly. Everything is predictable. Uranus is different. And here's where it gets weird, because different parts of Uranus rotate at different speeds. The interior of Uranus, the deep rocky and icy core that you can't observe directly, takes about 17 hours to complete one full rotation. That's the planet's true rotation period. But the upper atmosphere, the clouds and gas that you can actually see and measure, takes about 20 hours to complete a full rotation. That's a 3-hour difference. The outside is rotating slower than the inside. Or you could say the inside is rotating faster than the outside. That differential rotation, that speed difference between the interior and the atmosphere, is crucial to understanding why Uranus behaves so differently from the rest of the solar system. It creates enormous friction where the interior and atmosphere meet. It creates turbulence. It creates unusual wind patterns that scientists are still trying to fully understand. The differential rotation is like having two gears spinning at slightly different speeds, rubbing against each other, creating heat and disturbance. Except these aren't mechanical gears. They're layers of a planet, and the friction and shear forces between them generate wind patterns and atmospheric dynamics that continue to baffle researchers. The seasonal implications of this sideways rotation are almost incomprehensible when you think about them in detail. Because Uranus is tilted so extremely, 97.77 degrees, its seasons are not just unusual. They are the most extreme in the entire solar system. For about 21 Earth years, for 1/4 of a complete Uranian year, one entire pole of the planet is bathed continuously in sunlight. Imagine being at the North Pole of Uranus and having the sun never set for 21 years. Continuous daylight. The other pole exists in complete darkness. 21 years of perpetual daylight on one side. 21 years of perpetual night on the other side. Complete darkness. No sunset, no sunrise. Just blackness. Then the planet slowly rotates along its orbit, and the entire pattern reverses over the following decades. Uranus takes about 84 Earth years to complete one full orbit around the Sun, which is one Uranian year. That means a single season on Uranus lasts approximately 21 Earth years. 21 years is a very long time from the perspective of human life. You could be born during one season on Uranus and reach adulthood without ever experiencing a transition to the next season. You could live your entire life in a single Uranian season. Imagine living through a season on Earth that took longer than most human lifespans to transition. We're used to seasons lasting about 3 months each. We have 4 seasons a year. We experience seasonal changes constantly. On Uranus, you'd have 4 seasons, and each one would last longer than a human lifetime. The seasons would be so slow-moving that you might not notice them changing day to day or year to year. Changes would be measured on decadal timescales. Imagine being a human on Earth and having to endure 21 consecutive years of constant sunlight, never experiencing nightfall, or 21 consecutive years of constant darkness, never experiencing dawn. You'd go insane. The human circadian rhythm depends on day-night cycles. We'd lose track of time. We'd lose our biological rhythms. We'd be fundamentally disturbed by it. The atmospheric consequences of these extreme seasons are profound and far-reaching. The equatorial regions of Uranus experience rapid 17-hour day-night cycles during the equinox periods, when the sun is closest to being directly above the equator. During equinoxes, the equator actually experiences something approaching a normal day-night cycle. 17 hours of light, 17 hours of darkness, repeated. It's almost normal compared to the poles. But the polar regions experience decades of continuous light or continuous darkness. One pole has just finished an extended period of permanent night lasting decades. As the planet slowly transitions, that pole begins to experience the approaching sunlight. Eventually, it'll be bathed in permanent daylight for 21 years. Then that cycle repeats. This creates an atmospheric environment that is wildly dynamic and constantly changing, but changing on timescales that are geological rather than meteorological. Temperature gradients shift over decadal timescales, not daily timescales like on Earth. Pressure systems evolve over decades. Weather patterns develop and dissipate over years, not hours or days. Astronomers have only begun to understand these patterns through modern telescopic observations and data from the single spacecraft that has ever visited the planet. Voyager 2 provided a snapshot. Hubble has been providing long-term observations, but we're still learning. Nothing about Uranus's climate is stable in the way Earth's climate is stable. Everything about it is in constant slow-motion transition. The planet is always in the process of seasonal change, but that process takes decades. The atmosphere of Uranus is cold, brutally cold, incomprehensibly cold. Temperatures can drop to minus 224 degrees Celsius, which is minus 371 degrees Fahrenheit. Stop and think about that number for a moment. Minus 371 degrees. At that temperature, virtually all gases would liquefy. Carbon dioxide would be solid. Methane would be solid. Ammonia would be solid. Oxygen would be liquid. At this temperature, the periodic table itself starts to behave in ways we don't normally think about. This makes Uranus one of the coldest planets in the solar system, even colder than Neptune in some atmospheric layers, which is remarkable because Neptune is actually farther from the Sun. Uranus receives minimal solar radiation because it's so far from the Sun. The distance is 1.8 billion miles. The sunlight that does reach Uranus travels through 2 hours and 40 minutes of empty space before arriving at the planet. By the time it gets there, it's incredibly attenuated. It arrives as barely more than a whisper of heat. The solar intensity at Uranus is about 1/400th of what it is at Earth. Imagine standing outside on Earth in sunlight and feeling the warmth. Now imagine that warmth reduced to 1/400th of its strength. That's the solar intensity at Uranus. Yet despite receiving so little direct heat, Uranus's upper atmosphere still manages to do things that shouldn't be possible with that little energy input. The composition of the atmosphere is primarily hydrogen, about 83%, then helium, about 15%, and then a small but crucial fraction of methane, about 2.3%. That methane is crucial because it's what gives Uranus its distinctive color. When sunlight enters the atmosphere of Uranus, it gets scattered and reflected by the gas molecules. But the methane in the upper atmosphere absorbs the red portion of visible light, the wavelengths that correspond to what our eyes see as red. The methane absorbs those wavelengths and removes them from the reflected light. What bounces back, what reflects back toward space and toward Earth and toward telescopes, is the blue and green portions of the spectrum. The result is a striking pale bluish-green hue, almost cyan, that's unmistakable when you see it through a telescope. The planet looks alien. It looks profoundly wrong. It looks like something that shouldn't exist in our solar system. The hue is almost artificial. It's so clean. It's so pure. It's blue-green in a way that natural objects on Earth rarely are. And the simplicity of it, the purity of that color, is unsettling. It makes Uranus seem less real, less like a planet, and more like some kind of visual representation of a planet. The atmosphere isn't uniform either. Scientists have identified 4 distinct cloud layers in the troposphere, each at different pressure altitudes, each with different compositions. Methane clouds form at the top, around 1.2 bars of pressure, right at the upper boundary of the troposphere. Below that, at higher pressure, hydrogen sulfide and ammonia clouds exist at 3 to 10 bars of pressure. Ammonium hydrosulfide clouds layer below that, at 20 to 40 bars of pressure. And at the very bottom, deeper into the atmosphere where pressure is extreme, water clouds exist below 50 bars of pressure. That's a lot of cloud layers. That's a complex atmospheric structure. And here's the remarkable thing. Only the upper 2 cloud layers have ever been directly observed by spacecraft or telescopes. The lower layers, the ones at high pressure and high depth within the atmosphere, remain essentially unobserved. We know they theoretically exist based on our models and our understanding of planetary chemistry, but we've never actually seen them. We've never directly confirmed their existence, which means we know even less about the lower atmosphere than we do about the upper regions. The physics of planetary atmospheres at extreme pressure and extreme temperature is not something we have extensive observational data about. The frigid temperature persists despite the minimal solar input, which raises a fundamental question that has puzzled scientists for decades. If Uranus receives so little heat from the sun, why is it so consistently cold? Why doesn't it warm up at least a little bit? The answer is that it doesn't have internal heat to compensate. Uranus is not warming itself from the inside. Unlike Jupiter and Saturn, which radiate significant heat from their cores, Uranus is pretty much in thermal equilibrium with its environment. The coldness is the default state when you're that far from the sun and your planet doesn't generate its own warmth. Without internal heat, without solar heat, there's nothing to raise the temperature. The planet is cold, very cold. Winds on Uranus reach speeds of 560 miles per hour. 560, that's 900 kilometers per hour. Let me put that in perspective. That's faster than a Formula One race car. That's faster than the top speed of most commercial aircraft. A passenger jet cruises at around 550 miles per hour. Uranus's winds are slightly faster than that. These winds are the second fastest in the entire solar system, exceeded only by Neptune, which is the only other ice giant in the solar system. Neptune's winds are even more extreme, reaching over 600 miles per hour in some places. But Uranus is close behind. What's particularly strange and counterintuitive is that these extreme winds exist in a planet that looks visually calm and featureless, almost serene. The atmosphere appears peaceful, almost boring when you observe it through telescopes. There are no obvious storm systems. There are no visible hurricane-like structures. There's no great red spot. There's no dramatic banding. The planet just looks like a smooth, featureless, blue-green sphere. Yet underneath that apparent stillness, winds of extraordinary violence are tearing through the upper layers of the atmosphere. It's as if Uranus has learned to hide its violent nature beneath a calm exterior. It's as if the wind is happening invisibly. The wind patterns themselves are bizarre and counterintuitive. At the equator of Uranus, winds blow retrograde, which means backward, opposite to the direction the planet rotates. The planet is rotating one way, but the atmosphere at the equator is moving in the opposite direction. That doesn't make intuitive sense, but closer to the poles, winds shift to prograde, moving in the same direction as the planet's rotation. This latitudinal variation, this dramatic change in wind direction, depending on where you measure it, is one of many mysteries about Uranus that scientists have struggled to explain for decades. Think about the geometry here for a moment. The interior of the planet completes a rotation in 17 hours. The upper atmosphere takes about 20 hours. That 3-hour difference in rotational speed, multiplied across the entirety of a planet as massive as Uranus, creates enormous stresses and friction. The shear forces at the boundary between the interior and the atmosphere are immense. That friction, that shear, generates wind. It creates turbulence. It does all the things you'd expect friction to do when you're talking about a planet-sized object spinning at different rates. Wind is generated. Wind accelerates. Wind patterns develop. Wind continues to interact with the differential rotation. Yet we still don't fully understand the mechanism that drives these winds, maintains them, and creates the patterns we observe. There's clearly something going on that we don't completely understand. The presence of these extreme winds, despite the lack of visible storm systems, is deeply puzzling. This is completely different from Jupiter or Saturn. On Jupiter, you can see the great red spot, a storm system so large that you could fit Earth inside it. That storm system has been visible for hundreds of years. On Saturn, you see storm bands and turbulent regions that constantly evolve and change. You can watch them in real time as you observe the planet from one night to the next. On Uranus, the atmosphere looks featureless, almost boring. You're looking at a smooth blue-green sphere. Yet the winds are nearly as violent as anything Jupiter produces. It's like the violence is happening invisibly, hidden beneath a calm surface. It's like Uranus has learned to conceal its turbulent nature. And we don't have a good explanation for why. Now we reach perhaps the most perplexing mystery about Uranus. The question that has haunted planetary scientists for decades. The planet should be warmer than it is. The physics of planetary formation and planetary evolution tell us that planets should be warmer than Uranus is. All the giant planets emit some amount of heat from their interiors, heat that's left over from their formation, still radiating away from their cores billions of years after they were born. This is residual heat from the gravitational collapse that formed them. This is heat from the processes that built them. Jupiter, the largest planet in the solar system, radiates about twice as much energy as it receives from the Sun. Twice. That's an enormous amount of internal heat. Jupiter is warm. Saturn radiates about twice as much energy as it receives from the Sun as well. Saturn is also warm internally. Neptune, the other ice giant, radiates 2.61 times as much energy as it receives from the Sun. Neptune is actually warmer internally than Saturn, despite being farther from the Sun and receiving even less solar radiation. Those planets are warm inside. They generate heat internally. They warm themselves. Uranus, by contrast, emits almost the same amount of energy as it receives from the sun. Almost exactly the same. There's almost no internal thermal flux. The planet is not radiating excess heat. It's not warming itself from the inside. It's nearly in thermal equilibrium with its environment, which should not be possible based on everything we know about how planets work. An object as massive as Uranus should have residual heat. It should have heat left over from its formation. It should radiate that heat into space. Yet Uranus has almost none. The thermal output should be there, but it's not. This is one of the most perplexing mysteries in planetary science. It doesn't fit the model. It doesn't fit our expectations. It's an anomaly. Scientists have proposed various theories to explain this anomaly. Maybe the hypothesized giant collision that tilted Uranus, the massive impact by an Earth-sized protoplanet, also somehow stripped away the planet's internal heat, dispersing it into space during the collision. If you have an impact of sufficient violence, maybe it can release the heat from the planet's interior. Maybe there's some barrier, some layer in the planet's upper mantle or core that prevents core heat from rising to the surface. Maybe the internal structure of Uranus is so unusual that heat can't circulate the way it does in other planets. Maybe something else entirely happened that we haven't even considered yet. The truth is, nobody knows. Nobody has a definitive answer. The lack of internal heat is directly connected to why Uranus's atmosphere looks so calm and featureless compared to Jupiter or Saturn. It's cool. It lacks the thermal energy to drive visible storm systems. The winds are there. The extreme winds exist. But they're not powered by internal heat the way storms on Jupiter are powered by internal heat. They're atmospheric wind systems driven by something else, something we don't fully understand. Maybe differential rotation. Maybe the oblique angle of the sun. Maybe some other mechanism entirely. The mystery of Uranus's missing heat has puzzled astronomers for decades, from the discovery of the phenomenon to the present day, and continues to resist easy explanation or solution. It remains one of the great unsolved mysteries of planetary science, a fundamental question about how planets work and why Uranus is so different from all the others. Here's the problem with studying Uranus from Earth. It's extremely difficult. Beyond difficult. It's so faint. It's so far away. There are only so many observations you can make from Earth, only so much data you can gather before you hit the limits of what ground-based telescopes can tell you. The distance is just too great. The brightness is just too faint. The resolution you can achieve from the surface of Earth looking up at the sky through the atmosphere is limited. So, when NASA's Voyager 2 spacecraft visited Uranus in 1986, after traveling 1.8 billion miles through space over the course of 9 years, it represented an opportunity that may never come again. Think about that. 9 years to reach Uranus. 9 years of travel through empty space, and then Voyager 2 would pass by the planet and continue on its journey toward the outer solar system, and eventually out of the solar system entirely. The spacecraft had to do everything in a hurry. The flyby window lasted only about 6 hours. 6 hours. That's how long Voyager 2 had to observe Uranus as it passed by the planet. In 6 hours, the spacecraft had to collect as much data as it could about this mysterious planet and its system of moons and rings. It had to make detailed observations. It had to conduct measurements. It had to take thousands of images. And it had to do all of this at incredible speed, hurtling past the planet while moving at thousands of miles per hour, moving too fast to slow down or change course. It was a 6-hour window to study an entire planetary system. Despite the brief window, despite the constraints and the speed and the limited time, Voyager 2 accomplished remarkable things. It discovered 10 previously unknown moons orbiting Uranus, 10 new worlds that nobody had ever seen before. It discovered 2 new rings, adding to the already known ring system. It measured a magnetic field stronger than Saturn's, finding that Uranus had a surprisingly powerful magnetosphere despite its other unusual characteristics. It returned photographs and scientific data that still fuel discoveries today, nearly 40 years after the flyby. The data collected by Voyager 2 keeps giving. New analyses are still being published. New interpretations of the data continue to emerge. The spacecraft was remarkably capable for its time. Many of the discoveries that Voyager 2 made had to wait decades for confirmation by other instruments. The moons and rings that Voyager 2 discovered couldn't be definitively confirmed until the Hubble Space Telescope became operational and could observe Uranus with much better resolution. It took the Hubble Space Telescope, launched in 1990, to begin verifying what Voyager 2 had found and expanding upon those initial observations. Hubble has been studying Uranus for over 30 years now, constantly adding new information, discovering new rings, finding new moons, revealing new mysteries. The brief encounter with Voyager 2 remains humanity's only close-up glimpse of Uranus. It's the only time a spacecraft has ever flown near the planet. It remains the most intimate data we have about this world, the highest resolution observations, and the most detailed measurements. And it remains one of humanity's greatest achievements in planetary exploration. A moment when we reached out across the solar system and touched another world, if only for an instant. 6 hours of contact with an entire world. And from those 6 hours, we're still learning, 40 years later. The Voyager data kept revealing more surprises, and nowhere was that more apparent than in what they discovered about Uranus's magnetic field. Magnetic fields are supposed to work a certain way. They're supposed to align with a planet's axis of rotation. On Earth, the magnetic poles are roughly aligned with the geographic poles. Your compass points roughly toward the North Pole because the magnetic field is oriented the same way the planet spins. On Jupiter, the magnetic field is tilted a bit, but it's still reasonably aligned. On Saturn, same thing. There's some tilt, but nothing extreme. Then there's Uranus. Uranus doesn't follow the rules. Uranus's magnetic field is tilted at 59 degrees from the planet's axis of rotation. 59 degrees. That's more than a right-angle difference. That's a massive offset. It's as if Uranus's magnetic poles and geographic poles decided to point in almost completely different directions. But it gets worse. The magnetic field doesn't even originate from the geometric center of the planet. It's shifted. The magnetic dipole is offset from Uranus's center toward the south rotational pole by almost 1/3 of the planetary radius. 1/3. That's an enormous offset. It's like if you drew a line through Earth's center and tried to place our magnetic field, and the magnetic field started not from the center, but from a point 1/3 of the way toward one pole. It would be bizarre. It would be confusing. And that's exactly what's happening at Uranus. The consequences of this bizarre magnetosphere configuration are profound and strange. Different regions of Uranus experience vastly different magnetic field strengths. In the southern hemisphere, the magnetic field strength can be as low as 0.1 Gauss. In the northern hemisphere, it can be as high as 1.1 Gauss. That's an order of magnitude difference depending on where you measure it. That's not a subtle variation, that's a dramatic difference in magnetic environment. To understand how unusual this is, imagine if Earth's magnetic field was 10 times stronger on one side than the other. Imagine if a compass on one side of the planet would point in a completely different direction from a compass on the other side. That's closer to what's happening at Uranus. Most planets have magnetic fields that are relatively consistent across their surfaces, stronger at the poles and weaker at the equator, but following a predictable pattern. Uranus is unpredictable. Uranus is asymmetrical. The magnetic environment at one pole is radically different from the magnetic environment at the other pole. One hemisphere is heavily shielded from the solar wind by a strong magnetic field. The other hemisphere is barely protected. The protection is lopsided. The safety is asymmetrical. Particles that would be deflected away at one pole might reach down into the atmosphere at the other pole. This asymmetrical magnetosphere creates an unusual auroral pattern. On Earth, auroras occur at the magnetic poles in a ring-like structure circling each pole. You get the northern lights near the Arctic, the southern lights near the Antarctic, both of them forming these beautiful curtains of light centered on the magnetic poles. On Jupiter and Saturn, auroras form similar polar rings, beautiful bands of light centered on the magnetic poles. The pattern is consistent. The auroras appear where you'd expect them to appear based on where the magnetic poles are. On Uranus, the auroras don't follow that pattern at all, because the magnetic poles are offset from the geographic poles, because the magnetic field is tilted at such an extreme angle. The auroras don't form in the expected locations. They form in complex three-dimensional patterns that have nothing to do with the geographic poles. They form where the tilted magnetic field is strongest, which is not where you'd expect them to be based on the planet's rotation. The result is auroras that exist in bizarre locations, forming in places that have no obvious geometric relationship to the planet's axis of rotation. The aurora itself looks different on Uranus. The patterns are stranger. The colors are unusual. The dynamics are unlike anything we see on other planets. Scientists studying these auroras are discovering that they're influenced by the tilted magnetic field in ways that create unique atmospheric phenomena. Heat is being generated in unexpected locations. Charged particles are flowing in unusual patterns. The ionosphere, the charged region of the upper atmosphere where auroras form, is shaped by this tilted field in ways that produce three-dimensional structures, rather than the simple rings we see at other planets. The auroras are dynamic, constantly shifting as Uranus rotates and the tilted magnetic field rotates with it. Different atmospheric regions experience auroral activity as they rotate into alignment with the tilted field. The result is a dynamic, ever-changing auroral system that has surprised every scientist who has studied it. The tilted and offset magnetic field also means that Uranus's magnetosphere is hit by the solar wind in an extremely asymmetrical way. The solar wind is the constant stream of charged particles flowing from the sun. As the solar wind encounters a planet's magnetic field, it shapes the magnetosphere. It compresses the field on the day side, stretches it on the night side. On Earth, this creates a magnetosphere that's roughly teardrop-shaped, pointed toward the sun on one side and stretched into a long tail on the other side. On Uranus, with a tilted and offset magnetic field, the situation is chaotic. The magnetosphere is lopsided. It's not symmetrical. As Uranus rotates, and as the planet's tilted magnetic field rotates with it, different parts of the magnetosphere are being bombarded by the solar wind in different ways. One moment, a given hemisphere has a strong magnetic field facing the solar wind. A few hours later, due to Uranus's rotation, a weaker part of the field is facing the solar wind. This constant shifting of the magnetic field orientation means that the magnetosphere is constantly being reconfigured. It's constantly being reshaped by the solar wind. It's never in equilibrium. It's never stable. It's always changing, always readjusting, always responding to the solar wind hitting it at different angles and with different strengths. During intense solar flares, during moments of extreme solar activity, Uranus's magnetosphere can be squashed flat by the solar wind. The pressure of the solar wind can overcome the magnetic field's ability to shield the planet. When that happens, ions in the atmosphere can escape into space. the atmosphere can be stripped away. This is a process called magnetospheric erosion, and it happens to all planets with magnetic fields during strong solar events. But on Uranus, with its tilted and offset magnetic field, the erosion pattern is unusual. The atmosphere isn't stripped uniformly. It's stripped more from some regions than others. It's stripped more aggressively in some places because the magnetic field is weaker there. This creates a dynamic and constantly changing atmospheric loss process. Over time, over billions of years, this process can strip away significant amounts of atmosphere. It can change the composition of the upper atmosphere. It can fundamentally alter how the planet evolves. When Voyager 2 encountered Uranus in 1986, the solar wind was about 20 times more intense than normal. The spacecraft arrived during a period of high solar activity. A solar storm had pumped up the solar wind to extreme levels. The magnetosphere was compressed. It was being squashed by this elevated solar wind pressure. The situation was more chaotic than usual. This meant that Voyager 2's observations of the magnetosphere were made during an unusual moment. The spacecraft arrived at a moment when the magnetosphere was under extreme stress, when it was being compressed and reshaped by unusually powerful solar wind. The data collected was valuable, scientifically important, but it was an extreme case. It wasn't representative of normal conditions. For decades, scientists thought that Uranus's atmosphere was typically empty, that the solar wind normally stripped away most of the ionosphere. The Voyager 2 data seemed to indicate that the upper atmosphere was sparse, that most of the ionizable material was being blown away into space. But more recent observations using the James Webb Space Telescope and other instruments have revealed that the atmosphere is usually denser than Voyager 2 suggested. The spacecraft arrived at a bad time. The data was misleading. The true magnetosphere of Uranus is more complex, more variable, and more interesting than the Voyager data alone would suggest. It's a magnetosphere that's constantly responding to solar input, constantly being reshaped, constantly creating auroras and plasma dynamics that we're only beginning to understand. It's a magnetosphere that defies easy categorization, that refuses to fit the patterns we see at other planets, that maintains its own unique character despite our attempts to force it into familiar patterns. The magnetosphere changes from day to day as solar activity varies. It changes on hourly timescales as Uranus rotates and the tilted field rotates with it. It's a dynamic, responsive system that's never in equilibrium, never stable, always reacting to external forces in unexpected ways, moving away from the planet's magnetic environment and toward the structures that orbit within it. The ring system of Uranus presents another profound mystery. 13 rings encircle Uranus, 13 distinct bands of material held in orbit by gravity. But unlike the famous rings of Saturn, which are broad and spectacular and composed primarily of clean water ice, Uranus's rings are tightly confined. They're dense, they're narrow, they're more like a wreath around the planet than a sweeping skirt. The rings of Saturn spread out across tens of thousands of kilometers. You can see them from Earth with binoculars. The rings of Uranus are so confined and so narrow that they're almost invisible even to powerful telescopes. The question of why Uranus's rings are kept on such a tight leash is an ongoing mystery in planetary science. Some scientists think that small moons, moonlets too small to detect directly, might be shepherding the rings, using their gravitational pull to keep the particles from spreading outward. Other scientists think that the dynamics of Uranus's unusual magnetic field or gravitational field might be confining the rings. The truth is, nobody fully understands why the rings are so different from Saturn's rings. The chemical composition of Uranus's rings is equally mysterious. Scientists are flummoxed by what they're made of. The particles that make up Saturn's rings are primarily water ice, clean and bright. The ice is relatively pure. It reflects sunlight effectively. You can see Saturn's rings easily from Earth, even through modest telescopes. They're bright. They're unmistakable. They're among the most visually striking features in the solar system. Uranus's rings are different. They're extremely dark. They're among the darkest material in the entire solar system. The ice particles that make up the rings are not clean. They're contaminated with something. The contamination is what makes them so dark. Scientists think the material is composed of water mixed with organic compounds, complex carbon-based molecules that darken the ice. Or the rings might be blocks of methane ice that have been singed black by radiation or processed by collisions. The darkening mechanism is unclear, but the result is unmistakable. The rings are dark. They absorb light rather than reflecting it. The extreme darkness makes the rings very difficult to observe even with modern telescopes. For decades after Voyager 2 discovered them in 1986, scientists barely understood what they were looking at. The images from the spacecraft showed hints of rings, but the details were hard to discern. Only when the Hubble Space Telescope began serving the planet did the rings become visible enough to study in detail. Hubble has revolutionized our understanding of the rings. The telescope's superior resolution revealed structure that was completely invisible to Voyager 2. Hubble eventually discovered a largest ring, twice the diameter of the planet's previously known rings. New rings are still being discovered. New structure is still being revealed. The ring system is more complex than anyone initially suspected. Every time we observe Uranus with better instruments, we see more rings, more structure, more complexity. The rings also display multiple colors, which suggests different compositions in different rings. Observations made by Hubble and the Keck Observatory show that the outer ring of Uranus is colored blue, while inner rings are reddish or dusty gray. This color variation is deeply puzzling. Saturn's rings are composed almost entirely of water ice, so they're uniformly bright and white. Uranus's rings have varying colors, which means they have varying compositions. The blue coloration of the outer rings is particularly mysterious. Scientists don't know what chemical or mineral composition produces blue color in a ring system. When researchers are asked where the blue is coming from, they give honest answers. That's another mystery that is not solved. Nobody knows. The rings keep their secrets well. The proposed mechanism for how these rings are maintained and replenished involves the small moon Mab. Mab is a tiny moon, barely 10 kilometers across, a speck of a world orbiting inside the ring system. It's so small that if you were standing on Mab, the surface gravity would be almost nothing. You could jump off the surface and escape into space. Mab is too small to generate enough gravity to spray icy material into space on its own. Mab is too small to have geological activity that would create plumes or outgassing events. But asteroids are constantly bombarding Mab and all the other small moons in the Uranian system. Micrometeorites from space are constantly striking these small worlds. The impacts are relentless. They never stop. The bombardment is constant and ongoing. The impacts kick up material. Ice and rock are ejected into space. The ejected material goes into orbit around Uranus. This ejected material then forms the rings. This ejected material creates the ring structure that we observe. This is the proposed mechanism, and it's fascinating because it suggests that the rings are not static structures left over from the formation of the planet. The rings are dynamic systems constantly being replenished with fresh material from impact events. The rings are young, geologically speaking. They're not ancient structures that have persisted since the formation of the Uranian system 4.5 billion years ago. They're young. They're maintained by ongoing bombardment. They're kept fresh by constant input of new material from impact events on nearby moons. This is similar to what happens at Saturn, where the rings are fed by water plumes from the moon Enceladus. Saturn's moon Enceladus has geysers that spray water into space, and that water forms Saturn's rings. But at Uranus, there are no grand plumes. There's no active geology creating water fountains. There's just steady bombardment creating a steady supply of ring material from collisions. The rings are a continuous creation process rather than a static inheritance. Understanding exactly how this process works, exactly how the bombardment maintains the rings, exactly why the rings are confined so tightly, remains an open question in planetary science. The mechanics of how particles are kicked off MAB and how they form rings are not fully understood. Now to the moons themselves. Uranus has 28 known moons, 29 if you count the recent discovery in 2025. That's a lot of moons. But what makes Uranus's moon system genuinely unique is not the number of moons, it's the names. The moons of Uranus are named after characters from the works of William Shakespeare and Alexander Pope. Most planets have moons named after Greek or Roman mythological figures. Jupiter's moons are named after gods and lovers. Saturn's moons are named after gods and titans. Neptune's moons are named after sea gods. But Uranus's moons broke from that tradition entirely. Titania, Oberon, Ariel, Umbriel, Miranda, these are characters from Shakespeare's A Midsummer Night's Dream and The Tempest. They're not gods, they're not mythological beings, they're literary characters. This naming convention started with the earliest discovered moons and has continued through all subsequent discoveries. The literary theme has never been abandoned. Every new moon of Uranus gets a name from classical literature. This makes Uranus's moon system distinctive among the outer planets. It's the only planetary system whose moons are uniformly named after literature rather than mythology. It reflects the planet's association with classical culture during the era of its discovery. It's unusual. It's quirky. It's very Uranus. The major moons of Uranus are genuinely substantial worlds. Titania, the largest, is 1,578 kilometers in diameter. To put that in perspective, that's about half the diameter of Earth's moon. That's about 1/20th the mass of Earth's moon. Titania is the 8th largest moon in the solar system. It's a significant world. It's substantial. It's not a small thing. Oberon is nearly as large as Titania. It's almost the same size. The two largest moons are comparable in scale. Ariel and Umbriel are somewhat smaller but still substantial. These four major moons, along with Miranda, form a 5-moon system of irregular, ellipsoidal bodies. The shape tells you something important. These moons reached hydrostatic equilibrium at some point in their histories. That's a technical term that means they were massive enough and hot enough that their own gravity pulled them into a roughly spherical shape. They collapsed under their own gravity into rounded shapes. They were geologically active enough to deform into these shapes. That means they had heat inside. They had internal processes running. 4 of the 5 major moons show signs of internally driven geological processes. There's evidence of canyon formation, massive scarps that cut across the surface. There's evidence of past volcanism, regions where lava may have flowed in the distant past. There's evidence of tectonic activity, where the crust has been fractured and moved. These are not dead, inert lumps of rock. These are worlds with histories. These are worlds that underwent significant internal processing. They were warm inside. They had energy. They had geological activity. The geological diversity of the major moons suggests that they experienced different thermal histories, different evolutionary pathways, different processes that shaped them over billions of years. Some moons cooled faster than others. Some moons had more internal heat than others. Some moons experienced different tidal heating from Uranus's gravity. The result is 5 moons with 5 different geological stories. Studying these moons is like studying the history of the solar system, written in stone and ice across 5 different worlds. The inner moons of Uranus are different. They're smaller, they're darker. They share common properties with the rings themselves. They're made of material similar to the ring particles. The composition is consistent. The origin seems to be the same. They're collisional fragments, bodies born from the constant bombardment and breakup that characterizes the inner moon and ring system. When you smash rocks together hard enough, you create new rocks and debris. That's what's happening in the inner Uranian system. The inner moons are much younger than the major moons, possibly much younger. The 5 major moons might be primordial, born during the formation of the Uranian system 4.5 billion years ago. The inner moons might have been created in the recent geological past, within the last billion years or so, from collisions between older bodies. The difference in age is profound. It means the inner system is still actively evolving. It means new moons are still being created. It means the system is young and dynamic in an evolutionary sense. The inner system is active, it's dynamic, it's constantly creating new structure. New impacts create new debris. New debris forms new moons. The cycle continues. For a long time, the Uranian moon system seemed stable and well understood. The 5 major moons had been discovered in the 18th and 19th centuries. Nothing new was found for over a century. Then, Voyager 2 discovered 10 new small moons in 1986. Those discoveries expanded the known moon count dramatically. Hubble discovered more in subsequent decades. The telescope added to our catalogue. But no discovery had been reported in more than 20 years, until 2024. That represents a huge gap in our knowledge. For more than 20 years, we thought we knew all the moons of Uranus. We thought we had catalogued the entire system. We were wrong. That's when Scott Shepherd and colleagues announced the discovery of 1 new irregular moon using the Subaru telescope in Hawaii. S/2023 U1, discovered from observations made in 2023, was the first new moon discovery in over 2 decades. 1 moon, 1 world that had been orbiting Uranus in plain sight, waiting to be discovered. It was followed shortly after by even more discoveries. The James Webb Space Telescope found another moon in early 2025, bringing the total to 29. This moon is probably about 10 kilometers in diameter, barely visible even to the most powerful telescopes on Earth. Think about that. A world the size of a small mountain, orbiting a planet billions of miles away, so faint and so small that it took the James Webb Space Telescope to detect it. That's how many small moons orbit Uranus. That's how many worlds exist in the Uranian system that we barely know about. Each new discovery reveals that there are probably more moons we haven't found yet. Each observation with better telescopes reveals worlds that were completely invisible to previous generations. The Uranian system is richer, more complex, and more populated than anyone suspected. How many more moons are out there? Too small or too dark to detect even with current telescopes? Nobody knows. But probably more than we can imagine. We're discovering them faster now than we did before, which suggests there are many more still waiting to be found. Among all the moons of Uranus, 1 stands out as particularly strange and fractured. Miranda. Miranda is the innermost of the major moons, orbiting closer to Uranus than the other large moons. It's a relatively small moon, only about 470 kilometers in diameter, about 1/4 the size of Earth's moon. When Voyager 2 flew past Miranda, The spacecraft revealed a world that looked as though it had been put together with duct tape and prayers. That's the exact impression that geologists got when they first saw the images. Miranda's surface is one of the most bizarre and fractured landscapes in the entire solar system. There are massive canyons carved into the surface, canyons deeper than the Grand Canyon, canyons that extend for hundreds of kilometers across the moon's face. If you were standing at the bottom of one of these canyons and looked up, you'd see walls towering miles above you. The canyons don't form any coherent pattern. They cut across the surface in multiple directions, as if something has torn Miranda apart, and it's been reassembled haphazardly. They go this way, then that way, with no obvious logic. There are regions of extreme elevation. There are ridges that rise thousands of meters. There are plains that drop away into depths. The landscape is chaotic. It's jumbled. It makes no sense at first glance. Looking at Miranda is like looking at a world that's been through a catastrophe and never really recovered. Scientists believe that Miranda was once torn apart by gravitational stresses. As the moon orbited Uranus, the planet's gravity pulled on it with unimaginable force. The tidal forces were so strong that they exceeded the structural strength of the moon. Think about tidal forces for a moment. Tides on Earth are caused by the moon's gravity pulling on our oceans. The moon pulls harder on the near side of Earth than on the far side, creating bulges. Now imagine that same gravitational differential applied to a solid rocky moon orbiting much closer to a much more massive planet. The forces are orders of magnitude stronger. The difference in gravitational pull between the near side and far side of the moon becomes extreme. Miranda was being stretched. It was being compressed. The stresses were so intense that the moon's own gravity couldn't hold it together. Miranda was literally pulled apart. It was shattered into fragments. The pieces were torn loose from one another. Then, over time, these fragments were recombined by gravity. The pieces came back together slowly, reformed by their own mutual gravitational attraction, but they didn't reassemble in the original configuration. They came back together, but not in the way they were before. They reassembled randomly. They reassembled haphazardly. Some pieces might be upside down. Some pieces might be rotated. Some pieces might be missing entirely, ejected into space and lost. The result is a world that looks shattered. The surface is a record of catastrophic destruction and reassembly. Looking at Miranda is like looking at archaeological evidence of a cosmic disaster. The canyons that cut across the surface mark the boundaries between different fragments. The regions of extreme elevation mark places where fragments were shoved together at different angles. The chaotic terrain is the visible evidence of extreme violence. The scars never healed. The landscape remembers the violence. This history makes Miranda one of the most interesting moons in the solar system. It's not just a dead rock, it's evidence of extreme processes. It's a world that has survived something that should have destroyed it completely. It's a monument to the power of gravity and the resilience of matter. The extreme seasonal changes that Uranus experiences have profound effects on all its moons and on the ring system as well. For 21 years, one hemisphere of Uranus is bathed in continuous sunlight. The poles experience permanent day. Imagine being at the North Pole of Uranus and having the sun never set for 21 years. No sunset, no sunrise, no variation, just sunlight continuously. Then the opposite hemisphere experiences the opposite situation. Darkness. Complete darkness for 21 years. Continuous night. During this time, the temperature patterns across the Uranian system are extreme. Some regions are heated continuously for decades. Some regions experience continuous cold for decades. The thermal cycling is extreme. The pressure cycling is extreme. The atmosphere EKSP ands and contracts on decadal timescales. Pressure on the day side builds up as the sunlit hemisphere heats up. Pressure on the night side decreases as that hemisphere cools down. The difference in pressure drives winds. The same thermal cycling affects the moons. They experience extreme heating on one side, extreme cold on the other. They experience these extreme conditions for years at a time without relief. One hemisphere of each moon faces constant sunlight, while the other faces constant darkness. The temperature difference between the two sides must be extreme. The thermal stresses on the moon's surface must be significant. The ring particles also respond to this thermal cycling. They expand and contract with the temperature changes. They develop internal stresses. They might become more prone to collisions or breakup. The thermal cycling could cause small particles to shatter or larger particles to develop cracks that spread over time. The entire Uranian system is locked in extreme seasonal variations that last longer than human lifespans. The entire system is slowly transitioning from one season to the next over timescales measured in decades. This is a world in slow-motion seasonal transition. This is a system locked in extreme variability that never resolves into stability. The ring particles are expanding and contracting on decadal timescales, developing internal stresses that might trigger collision cascades. The moons are experiencing tidal heating variations as their orbits shift with the planet's changing orientation. The entire system is a slow-motion dance that most planetary systems never experience. One particularly interesting aspect of the seasonal extremes is how they affect atmospheric circulation and weather patterns across Uranus. The extreme seasons create extreme temperature gradients. For decades, one hemisphere is heated while the other is frozen. The sun pours down on one pole continuously while the other pole sits in complete darkness. This creates enormous pressure differences in the upper atmosphere. On the day side, the atmosphere heats up. Air expands. Pressure increases. On the night side, the atmosphere cools. Air contracts. Pressure decreases. The difference in pressure drives winds. The wind tries to equalize the pressure by moving air from the high-pressure region to the low-pressure region. These pressure differences create storm systems. They create circulation patterns. Yet despite the extreme seasonal heating, despite the extreme temperature gradients that should create dramatic visible weather, Uranus's atmosphere looks visually calm. There are no obvious storm systems visible. There are no hurricane-like structures. There are no great red spots like Jupiter has. There are no visible bands like Saturn has. There are no white cloud formations towering in the upper atmosphere. The atmosphere appears featureless. It appears smooth. It appears serene. Yet the winds reach 560 miles per hour. Yet the velocities are extreme. This contrast between the apparent calmness of the atmosphere and the violence of the winds is one of Uranus's great mysteries. The wind exists, but it hides itself. The storms exist, but they're invisible. The circulation is extreme, but the appearance is serene. It's profoundly counterintuitive. How can a planet have winds that rival the strongest storms in the solar system, yet appear so peaceful and calm? Scientists don't fully understand why Uranus's atmosphere looks so calm despite being so turbulent. That's part of what makes the planet so puzzling. The atmosphere is doing extraordinary things, but it's not showing them visually. Something about the chemistry, the temperature structure, or the composition of the upper atmosphere is suppressing visible cloud formation while still allowing extreme winds to persist. Something about the seasonal cycling is maintaining winds without creating visible storms. Maybe the clouds don't form at the altitudes where the winds are strongest. Maybe the circulation happens below the visible cloud layers. Maybe the atmosphere is so transparent that even the most violent winds leave no visible trace. The mystery remains unsolved. The winds blow silently across a featureless face. One spacecraft, That's all humanity has ever sent to Uranus. 1. After traveling more than 1 billion miles through the solar system, after 9 years of journey time, Voyager 2 arrived at Uranus in 1986 and spent approximately 6 hours conducting close observations of the planet. 6 hours. That's less time than a transatlantic flight. That's barely enough time to accomplish anything meaningful in the conventional sense. Yet, in those 6 hours, Voyager 2 revolutionized our understanding of Uranus in ways that scientists are still unpacking nearly 4 decades later. The spacecraft approached from the sunlit side, the day side of the planet, gathering images and scientific data as it streaked past at enormous velocity. It couldn't slow down. It couldn't hover. It couldn't return for a second look. There was only one pass, one opportunity, one brief moment of close contact with this distant world. The Voyager 2 team made the most of it. Think about that for a moment. You've got one shot. You have designed a spacecraft, sent it across billions of miles of empty space, and now you have 6 hours to gather all the data you're ever going to get from this world. That's the pressure that the Voyager 2 team operated under. Every frame of film, every measurement, every observation had to count. You couldn't redo observations if something went wrong. You couldn't wait for better conditions. You had one moment, one opportunity, and the success or failure of the entire mission depended on how well you used those hours. The spacecraft was loaded with instruments specifically designed to gather as much information as possible during that brief encounter. Cameras captured images at different wavelengths, revealing details visible only in certain parts of the electromagnetic spectrum. Some instruments looked in ultraviolet light, revealing things invisible to human eyes. Others looked in infrared, detecting heat radiation. Some instruments used visible light, what we'd see if we were there looking at the planet. Magnetometers measured the planet's magnetic field with incredible precision, tracking the three-dimensional structure of the magnetic environment. Particle detectors tracked charged particles flowing from the sun, measuring the solar wind, detecting how it interacted with Uranus's magnetosphere. Radio transmitters beamed data back to Earth at light speed, taking more than 2 hours to arrive. By the time the first images of Uranus reached Earth, the spacecraft was already past the planet, already receding into the distance. Every second of that 6-hour window was used to collect information. There was no time wasted. There was no slack in the schedule. Scientists on Earth orchestrated the observations from control centers, sending commands that would take hours to reach the spacecraft. When Voyager 2 actually received those commands, the spacecraft was already responding to earlier commands, already 3 hours ahead of what Earth control was directing. It was a game played at light speed, with moves that couldn't be adjusted if something unexpected happened. If something went wrong during the encounter, there was no one there to fix it. The spacecraft had to handle problems autonomously, make decisions without ground support, continue collecting data despite whatever challenges arose. Voyager 2 discovered 10 new moons orbiting Uranus that no astronomer had ever seen before. 10 new worlds, previously unknown to humanity, revealed in those few hours. These weren't small discoveries, barely noticeable specks at the edge of detection. They were real worlds, genuine objects with measurable sizes and orbital characteristics. Some were large enough to have distinctive features. Others were small, just lumps of rock and ice, but still real bodies orbiting the planet. The spacecraft also discovered rings that had been theorized but never confirmed. Scientists had suspected that Uranus might have rings similar to Jupiter and Saturn, but no one had ever observed them directly. The evidence for their existence was indirect, based on observations of stellar occultations, times when Uranus passed in front of distant stars. Those observations hinted that something was blocking starlight, But the evidence wasn't definitive. Voyager 2 provided confirmation. 2 new rings entered the catalogue, and subsequent observations revealed even more rings that Voyager 2 had either missed or that weren't clearly visible in the data. And then there was the magnetic field discovery, the one that nobody expected, the one that rewrote textbooks about how planetary magnetospheres work. The magnetic field turned out to be tilted and offset in ways that violated conventional assumptions about how magnetic fields operate on planets. The Voyager observations were remarkable not just for what they found, but for what they implied about what remained unknown. The spacecraft revealed a world that didn't fit existing models of how ice giants should behave. The atmospheric dynamics didn't match predictions. The magnetic field configuration was bizarre. The ring system was more complex than anticipated. Every answer Voyager 2 provided seemed to generate 3 new questions. Scientists spent decades trying to interpret the 6 hours of data. They're still discovering new details in the archive. Images that seemed unremarkable when first analyzed later revealed subtle structures that scientists had missed. Technical advances in image processing allowed researchers to extract information that earlier scientists couldn't access. It was like finding new data without sending another mission. Voyager 2 essentially transmitted a time capsule of information that keeps yielding discoveries as our technological capabilities improve. The Voyager 2 magnetosphere data was collected during an unusual moment, and that moment colored interpretation of the findings for decades. The solar wind was about 20 times more intense than typical when Voyager 2 arrived at Uranus. A solar storm had elevated solar activity to extreme levels. The magnetosphere was compressed, squeezed by this elevated solar pressure. Ions that normally existed in the ionosphere were being blown away into space faster than usual. Scientists initially thought that Uranus was a particularly windy place, that its upper atmosphere was more empty and sparse than it actually was. Decades later, when better telescopes and instruments arrived, when the James Webb Space Telescope could observe Uranus in detail, scientists realized that Voyager 2 had arrived at a bad time. The spacecraft's data didn't represent typical conditions. It represented an extreme event, an unusual moment captured and mistaken for normal circumstances. This is a humbling reminder that a single observation, no matter how detailed, can mislead if you don't understand the context in which it was made. That lesson has guided planetary science ever since. Whenever you have only one snapshot of a system, you have to be extraordinarily careful about interpreting what that snapshot means. The question of why the auroras on Uranus form where they do requires understanding how the tilted and offset magnetic field interacts with the solar wind and the ionosphere. Auroras form when charged particles from the Sun encounter a planet's magnetic field and are guided down into the atmosphere. Think of the magnetic field as an invisible funnel, a 3-dimensional structure that channels particles from space down into the upper atmosphere. Charged particles from the Sun, traveling in the solar wind, encounter this funnel and are guided along its walls, funneled toward particular regions where they collide with atmospheric molecules, creating the glow we see as auroras. On Earth, those particles are guided toward the magnetic poles, which are roughly aligned with the geographic poles. The result is auroras that form in rings around the Arctic and Antarctic. You can see them near the poles, in latitudes where the magnetic field naturally channels particles into the atmosphere. The aurora forms a ring because the magnetic field structure creates a funnel that's narrowest, most efficient at guiding particles, in high-latitude regions near the magnetic poles. Most of the particle energy gets deposited in those regions, creating concentrated, visible glows. On Jupiter and Saturn, the same principle applies. The auroras form where the magnetic field funnels particles, which happens to be near the magnetic poles, which are reasonably aligned with the geographic poles. The auroras appear in expected locations. You can predict where the auroras will appear based on knowing where the magnetic poles are. On Uranus, this logical pattern breaks down completely. Because the magnetic field is tilted at 59 degrees from the axis of rotation, and because the magnetic dip, oddities, is offset from the planetary center. The places where particles are funneled down into the atmosphere are not anywhere near the geographic poles. They form in strange three-dimensional patterns. They appear in latitudes that have no obvious relationship to the planet's rotation. The auroras end up in weird locations, in places that would astonish astronomers studying Earth's or Jupiter's auroras. Imagine if Earth's auroras didn't appear in the Arctic and Antarctic. Imagine if they appeared instead at the equator, or at randomly distributed latitudes that changed as the planet rotated. Imagine trying to predict where Earth's auroras would appear without any logical geographic pattern. That's what Uranus's auroras are like. The pattern seems chaotic, seems random, until you understand that it's being controlled by a magnetic field that's tilted and offset in a way that no other planet in the solar system matches. The heat generated by those incoming particles creates an ionosphere that's structured very differently from what we see at other planets. Temperature gradients are extreme. Density variations are dramatic. The ionosphere becomes sculpted into three-dimensional patterns by the tilted magnetic field. As Uranus rotates, different atmospheric regions rotate through the region of strongest auroral activity. Different latitudes experience intense particle bombardment at different times. The result is a dynamic, constantly shifting auroral system. The auroras brighten and fade as the planet rotates, as different regions move into alignment with the tilted magnetic field structure. The colors are unusual. The patterns are strange. The relationship between the auroras and the planet's magnetic field geometry is unlike anything we see elsewhere in the solar system. Scientists are still working to understand exactly how the three-dimensional magnetic field structure creates the auroral patterns that have been observed because the connection is not straightforward. The tilted and offset field doesn't simply guide particles in a simple, predictable way. The geometry creates complex interactions. Plasma dynamics in the ionosphere create their own structures. Waves propagate through the ionosphere, influenced by the magnetic field. The result is an auroral system that resists simple explanation. Recent observations using the James Webb Space Telescope have revealed that Uranus's upper atmosphere is cooling. The trend has been ongoing since the early 1990s. The upper atmosphere is getting colder, radiating more energy to space than it's receiving from the sun. The average temperature is around 426 kelvins, about 150 degrees Celsius. That's already brutally cold, but it's getting colder. Every decade, the measurements show lower temperatures. Scientists don't understand why this is happening. What mechanism could be extracting heat from the upper atmosphere? The sun certainly isn't getting dimmer. Uranus isn't getting farther from the sun. The seasonal cycle doesn't explain the trend because the cooling has been consistent across the seasonal variations. Something about the composition of the upper atmosphere, something about the chemistry, something about the dynamics of the ionosphere and magnetosphere interaction is causing ongoing heat loss. The mystery deepens because we have only limited baseline measurements. Voyager 2 measured temperatures in 1986. Ground-based telescopes measured temperatures throughout the 1990s and 2000s. Now Webb is measuring temperatures again. The trend is unmistakable, but explaining it requires understanding atmospheric physics that we don't yet fully grasp. The internal structure of Uranus remains theoretical because we've never directly measured it. We don't have seismic stations on Uranus measuring earthquakes, listening to vibrations traveling through the planet's interior. We don't have boreholes drilling down toward the core, bringing back samples of the material beneath the clouds. We have only indirect evidence and mathematical models built on assumptions, educated guesses based on limited data. The standard model proposes 3 layers, a simplified division of the interior into regions with different properties. There's a rocky core in the center, composed of silicates and iron-nickel, similar in composition to terrestrial planets like Earth. This core is relatively small, only about 0.55 Earth masses, only about 1/10 the mass of Earth itself. Its radius is less than 20% of the planet's total radius. Around this core sits an icy mantle, and here the term ice is misleading, because it conjures images of frozen water, of ice like we know it on Earth. This isn't ice in the conventional sense, not frozen water at the surface, not water in a solid state that you could touch. This is hot ice, superheated under immense pressure. Water molecules stripped of their normal structure by extremes of temperature and pressure that transform them into states that have no analogue in our experience. The mantle comprises most of Uranus's mass, about 13.4 Earth masses, most of what the planet is. It's composed of water, methane and ammonia, all existing as hot, dense fluids under pressures that would be unimaginable on Earth. The density is extreme. The molecules are compressed until they're squeezed so tightly together that their electronic structures overlap. Outside this icy mantle is the gaseous atmosphere, hydrogen and helium mostly, extending outward for the last 20% of the planet's radius. The temperature at the core is estimated at about 5,000 kelvins, roughly the same temperature as the sun's surface, hot enough that matter at that temperature would glow if you could see it. The pressure at the core is 8 million bars, 800 gigapascals. To put that in perspective, the deepest point on Earth's ocean floor experiences pressure of about 1,000 bars. The Earth's center experiences pressure of about 360,000 bars. Uranus's core experiences pressures that dwarf Earth's center. That's pressure so extreme that the state of matter becomes fundamentally different from anything we encounter in our everyday experience. Atoms lose their electrons, becoming plasma rather than atoms in the conventional sense. Matter becomes ionized. Electrons can no longer orbit nuclei in discrete orbitals the way they do in normal atoms. The distinction between different states of matter becomes blurred: solid, liquid, gas. These categories break down when you're dealing with matter at such extremes. The internal structure that scientists propose is based on models, on assumptions about how the planet must be composed to explain its observable characteristics. The mass is known. The radius is known. The gravitational field has been measured. Using those constraints, scientists can calculate what internal structure would produce the observed gravity field. But this calculation is not unique. Different interior models can produce nearly the same gravitational signature. We don't know for certain whether the core is really rocky, or whether it's primarily composed of heavy ices and silicates mixed together. We don't know whether the mantle is layered, whether there are distinct boundaries between regions of different density and composition, or whether it's a gradual transition from one state of matter to another. We don't know whether the icy mantle is actually solid, or whether it's partially or entirely liquid. At those temperatures and pressures, the classical distinction between solid and liquid becomes meaningless. Matter exists in states that have no ordinary analogue. What makes the Uranus interior structure debate particularly challenging is the low internal heat, the mysterious lack of thermal emission. Jupiter radiates about 1.7 times as much energy as it receives from the Sun. Saturn radiates about twice as much. This excess heat comes from internal sources, from the slow contraction of the planet, from radioactive decay in the core, from leftover heat from the planet's formation 4.5 billion years ago. Neptune, almost identical to Uranus in size and composition, radiates 2.6 times as much energy as it receives from the Sun, but Uranus barely radiates any excess heat. The planet is nearly in thermal equilibrium with its surroundings. It receives energy from the Sun and radiates roughly the same amount back to space. There's no mystery excess. There's no obvious internal heat source. Scientists have proposed various explanations. Maybe the giant collision that tilted Uranus also stripped away its internal heat, dispersing the thermal energy that would otherwise remain. Maybe an internal barrier prevents heat from traveling upward from the core. Maybe the composition is different from Neptune's, producing less radioactive heating. Maybe the planet simply cooled faster for some unknown reason. None of these explanations are satisfactory. None of them fully account for the observed heat budget. The lack of internal heat likely contributes to the featureless appearance of the upper atmosphere. Without vigorous internal convection, without plumes of hot material rising from deep inside the planet, the upper atmosphere remains relatively calm. Clouds don't form with the same vigor that they do at Jupiter, where internal heat drives active atmospheric circulation. The winds at Uranus are extreme, but they don't create the visible storm systems that dominate Jupiter's appearance. The atmosphere looks bland, empty, featureless. The lack of visible structure belies the extreme velocities occurring at altitude. Everything about Uranus's internal heat budget is backwards from what we'd expect. The planet should be hot inside. It should be radiating significant excess heat. Instead, it sits in thermal equilibrium, puzzling scientists who have no good explanation for why this particular ice giant behaves so differently from its nearest neighbor. The composition of Uranus's atmosphere remains incompletely understood despite decades of observation and sophisticated analysis techniques. We know the basic components with reasonable confidence. Hydrogen dominates about 83% of the atmosphere. Helium comes second, about 15%. Methane comprises the remaining 2% or so. Methane is what gives Uranus its blue-green color, absorbing red light and reflecting blue light back into space. The methane is abundant enough that it visibly colors the entire planet. But below those primary components, below hydrogen, helium, and methane, the atmosphere becomes mysterious. We're confident these three exist, but everything else is uncertain. Ammonia should be present based on planetary formation models, but we don't see as much as predictions suggest should be there. Hydrogen sulfide should exist at certain altitudes where conditions are right for its formation, but its presence is difficult to confirm observationally. Water vapor should be present in the lower atmosphere, but direct observations are limited by our ability to see deep into the planet. Other chemical compounds, complex organic molecules, might exist in trace amounts, but detecting them from such a distance is extraordinarily challenging. The problem is fundamental. When light from the Sun bounces off Uranus and travels back to Earth, it passes through the planet's atmosphere twice. That light interacts with atmospheric molecules. Certain wavelengths are absorbed by those molecules. Others are reflected. By analyzing which wavelengths are present in the reflected light and which are missing, scientists can determine what's in the atmosphere. But the analysis requires knowing exactly what the atmosphere contains to predict what the light absorption pattern should look like. It's a circular problem. You need to know the composition to predict the observations, but you need the observations to determine the composition. Breaking this circle requires multiple independent lines of evidence, multiple different observation techniques, multiple ways of looking at the problem from different angles. When different methods agree, you have confidence in the result. When different methods disagree, you're left uncertain about which answer is correct. The James Webb Space Telescope is providing new compositional data that previous instruments couldn't access. Webb observes in infrared wavelengths heat radiation rather than visible light. This allows detection of temperature gradients, thermal emission from different atmospheric layers, heat sources that would be invisible in visible light. Webb is revealing details about the vertical structure of the atmosphere, the temperature profile, the composition at different altitudes. But even Webb's observations are limited by the fundamental challenge that Uranus is distant, faint, and small. You can't resolve tiny details on the surface or in the atmosphere. You can see the planet as a whole, measure its bulk properties, detect large-scale features. But fine details, small-scale structures, localized compositions, these remain beyond observation. Understanding Uranus's composition will probably require direct investigation, a spacecraft visiting the planet carrying instruments that can measure atmosphere from close range. The rotation rate of Uranus is itself somewhat mysterious, though in a different way than the magnetosphere or the internal heat. The planet's interior rotates with a period of about 17 hours. That's the rotation rate that was measured by tracking magnetic field variations, watching the magnetic field oscillations as the planet rotated. The magnetic field is anchored to the interior, rooted in the conducting layers of the planet's interior. As the interior rotates, the magnetic field rotates with it. By tracking how the magnetic field changes as it rotates, scientists can determine how fast the interior is rotating. But the upper atmosphere rotates faster. The atmosphere completes a rotation in about 14 hours, 3 hours faster than the interior. That's a significant difference. The atmosphere is moving about 20% faster than the planet's interior. Different latitudes rotate at different speeds. The equatorial atmosphere moves fastest. The polar regions move slower. This differential rotation is common among planets with gaseous atmospheres. Earth's atmosphere doesn't rotate with the solid surface either. Sometimes wind patterns cause regions of the atmosphere to move faster or slower than the solid surface beneath. But on Uranus, the velocity differences between atmosphere and interior are larger than on other planets. More pronounced, more dramatic. The atmosphere is decoupled from the interior. It's not locked to the solid body beneath by friction or magnetic forces. It's sliding over the interior, moving independently. This decoupling raises questions about how atmospheric dynamics work on Uranus. What's driving the circulation? What's maintaining the separation? The winds we observe, the speeds of 560 miles per hour, are these winds measured relative to the interior rotation or relative to the atmosphere's mean rotation rate? When scientists describe the winds, which reference frame are they using? The ambiguity matters because it affects interpretation. If you're measuring wind speeds relative to the rotating atmosphere, you get one set of values. If you're measuring relative to the interior, you get different values. When you're trying to understand the energy sources driving the winds and the mechanisms that maintain them, using the wrong reference frame gives you the wrong answers. The question of why Uranus's rotation period wasn't definitively known for so long is itself interesting. Earth's rotation is obvious. The sun rises and sets every day. You can observe rotation directly. Jupiter's rotation is visible. Bands in the atmosphere rotate with different periods at different latitudes, but you can measure the period by watching the bands go around. Saturn's rotation is visible. The rings and cloud bands provide reference points, but Uranus is featureless. There are no obvious features to track as the planet rotates. No bands, no storm systems, no clouds that persist long enough to serve as rotation markers. Without a feature to follow, how do you measure rotation? Scientists had to rely on magnetic field variations, measuring how the magnetic field oscillates as the tilted, offset magnetic poles rotate past observation points. But magnetic field measurements have their own ambiguities, their own interpretive challenges. Different scientists analyzing the same data got somewhat different rotation periods. It wasn't until multiple independent measurements from different instruments on different spacecraft and from ground-based radio observations that the rotation period converged on the 17-hour value that's currently accepted. Future observations of Uranus will probably require sending another spacecraft. Ground-based telescopes have reached their limits in what they can accomplish. Even the most powerful instruments, even the James Webb Space Telescope, with its extraordinary capabilities, are constrained by distance and by the planet's inherent faintness. Uranus is small as planets go, and it's so far away that even the most sensitive detectors struggle to gather detailed information. The Hubble Space Telescope has done remarkable work over the decades, discovering rings, tracking atmospheric changes from year to year, monitoring the auroras as they shift and evolve. But there's only so much you can learn about a planet by looking at it from 8 billion kilometers away. You can see the planet as a whole, as a unit. You can measure bulk properties, the total mass, the total brightness, the radius. You can detect changes from year to year. Watch how the atmosphere evolves over decades. But you can't investigate the details that reveal how the planet actually works internally. You can't measure the composition at depth, in the regions below the visible clouds. You can't explore the magnetosphere in detail, mapping out its three-dimensional structure in the way it truly exists. You can't understand the atmospheric circulation at the scales where it actually happens, watching how individual storms develop and dissipate, how weather patterns move across the planet. You can't study the moons up close, see their surfaces in detail, understand their geological histories. Understanding Uranus fully, understanding it not just as a collection of puzzles but as an integrated system, requires going there, sending a spacecraft to investigate the planet directly. Several missions have been proposed over the decades. Some proposals suggest an orbiter, a spacecraft that would enter Uranus orbit and remain in the system for years, observing the planet continuously, visiting the moons, mapping the magnetosphere. An orbiter could make observations that would be impossible from Earth, revealing seasonal changes as the planet progresses through its extreme seasonal cycle, documenting how the magnetosphere evolves, tracking atmospheric weather patterns that develop and dissipate. Other proposals suggest probes that would drop into the atmosphere, measuring composition, temperature, pressure, wind speed, and other properties directly as they descended. An atmospheric probe would provide data that no remote observation could match. The probe would experience the atmosphere firsthand, sampling gases, measuring particle concentrations, experiencing the conditions directly. The data returned would revolutionize our understanding of Uranus's atmospheric structure and composition. The cost of such a mission would be enormous. Launching a spacecraft, traveling the vast distance to Uranus, which takes many years of journey time, requires fuel and equipment, all of which must function reliably over that extended journey through the harsh vacuum of space. Once the spacecraft arrives at Uranus, years after launch, operating it at such a distance means communication delays measured in hours. Commands sent from Earth take hours to arrive. Responses take hours to return. The spacecraft must operate with increasing autonomy, making decisions without waiting for ground control, without the possibility of real-time human intervention. The engineering challenges are severe and multifaceted. Building a spacecraft that can function reliably for the decade-long journey is possible, but extraordinarily expensive. The spacecraft must survive cosmic radiation, withstand the vacuum, endure extreme temperature fluctuations, and maintain its systems in working order despite years of exposure to the space environment. Building instruments that can withstand the extreme environments around Uranus requires specialized design and extensive testing. Surviving radiation belts, cosmic rays, extreme temperatures, and other hazards of deep space requires redundancy in all critical systems, shielding from radiation, and engineering that pushes technology to its limits. No space agency has committed to a dedicated Uranus mission despite the scientific merits. The focus has been on other destinations that seem more politically viable or scientifically urgent in the moment. Mars receives rovers and orbiters, capturing public imagination with the search for past life. The Moon has exploration programs backed by international competition. Jupiter has received the Juno orbiter, which is currently operating and providing data. Saturn had the Cassini-Huygens mission, one of the most successful planetary missions ever conducted, which revealed the system in extraordinary detail. But Uranus remains the least explored major planet in the solar system. Only one spacecraft has ever visited. No dedicated mission is currently approved, funded, or under development. The political and budgetary priorities have directed resources elsewhere, toward destinations that seemed more achievable or more urgent at the time. Yet the scientific case for returning to Uranus is compelling. The planet is a paradigm, an example of an ice giant, a category of planet that's common around other stars. Understanding ice giants at Uranus is understanding a category of worlds that appears frequently throughout the galaxy. If humanity ever develops the capability to visit exoplanets, if we ever encounter planets orbiting distant stars, many of them will be ice giants similar to Uranus. Understanding how ice giants work, understanding their atmospheres, their interiors, their magnetospheres, provides context for understanding worlds we'll encounter in the future. The extreme axial tilt on Uranus provides a unique laboratory for studying how extreme seasons affect planetary systems. Nowhere else in our solar system can you find such extreme seasonal variations. Studying how Uranus's atmosphere responds to such extreme seasons provides insights that apply to understanding climate on any planet experiencing extreme seasonal variations. The low internal heat on Uranus raises fundamental questions about planetary cooling, about heat loss mechanisms, about long-term thermal evolution. Understanding why Uranus is anomalously cool compared to Neptune would illuminate principles of planetary physics that apply to planets throughout the universe. The magnetosphere configuration, tilted and offset, creates a unique example of how magnetic fields interact with solar wind and atmospheres. Understanding Uranus's magnetosphere reveals physics that might apply to planets with unusual magnetic field configurations. The moons orbiting Uranus represent another compelling target for exploration. The 4 largest moons might harbor subsurface oceans, liquid water beneath their surfaces where life might exist. No exploration of those moons has been conducted beyond the Voyager 2 flybys. The moons remain virtually unknown. If Uranus is ever revisited, the moons should be investigated thoroughly. Each moon tells a geological story. Miranda's shattered surface reveals tidal forces in extreme. The other major moons show signs of past geological activity. Their histories could illuminate how ice giant moons evolve, how tidal heating affects their geology, how they interact with their parent planet. The ring system itself, mysterious and poorly understood, would benefit from close investigation. Understanding how the rings form, how they're maintained, what they're composed of, would require detailed observations impossible from Earth, or from the rapidly passing perspective of a spacecraft conducting a brief flyby. Yet the scientific case for returning to Uranus is compelling. The planet is a paradigm, an example of an ice giant, a category of planet that's common around other stars. Understanding ice giants at Uranus is understanding a category of worlds that appears frequently throughout the galaxy. If humanity ever develops the capability to visit exoplanets, if we ever encounter planets orbiting distant stars, many of them will be ice giants similar to Uranus. Understanding how ice giants work, understanding their atmospheres, their interiors, their magnetospheres, provides context for understanding worlds we'll encounter in the future. The extreme axial tilt on Uranus provides a unique laboratory for studying how extreme seasons affect planetary systems. Nowhere else in our solar system can you find such extreme seasonal variations. Studying how Uranus's atmosphere responds to such extreme seasons provides insights that apply to understanding climate on any planet experiencing extreme seasonal variations. The low internal heat on Uranus raises fundamental questions about planetary cooling, about heat loss mechanisms, about long-term thermal evolution. Understanding why Uranus is anomalously cool compared to Neptune would illuminate principles of planetary physics that apply to planets throughout the universe. The magnetosphere configuration, tilted and offset, creates a unique example of how magnetic fields interact with solar wind and atmospheres. Understanding Uranus's magnetosphere reveals physics that might apply to planets with unusual magnetic field configurations. When you compare Uranus to the other planets in our solar system, it becomes immediately clear that Uranus occupies a category of its own, something genuinely different from what we see elsewhere. Neptune is its closest relative, and this is where the comparison becomes most illuminating. Neptune is similar in size, similar in composition, made of ice and rock and gases, in roughly equivalent proportions. The two planets should be twins, should behave similarly in almost every way. Yet Neptune behaves dramatically differently from Uranus in nearly every meaningful measurement. Neptune radiates heat that it shouldn't have, excess thermal energy that violates expectations, that contradicts our models of planetary cooling. Neptune's winds are more violent and more visible, producing dramatic storm systems that astronomers can observe easily. Neptune's internal structure remains as mysterious as Uranus's, but the heat flow is opposite, the thermal behavior inverted. This comparison is crucial because it forces scientists to ask what makes Uranus different. The collision hypothesis might explain the axial tilt, that catastrophic impact that knocked Uranus onto its side. It might explain the low internal heat if the impact was violent enough to strip away thermal energy, to scatter the heat that would otherwise remain trapped inside the planet. But it doesn't completely explain everything, not in a satisfactory way. There are gaps in the explanation, inconsistencies that make scientists uncomfortable. Jupiter and Saturn are much larger, much more massive, composed primarily of hydrogen and helium rather than water and ammonia. Their internal heat is more robust, stronger, more vigorous. Their atmospheres are more active, more dynamic, with visible storm systems and elaborate cloud structures. Their magnetospheres are larger and more complex, extending farther into space, with stronger field strengths. Yet the underlying physics should be similar. You compress hydrogen and helium enough, you get the conditions on Jupiter. You work with a smaller mass of different materials, you get something like Uranus or Neptune. The transitions should be smooth. They should be predictable based on basic principles of physics and planetary science. Instead, Uranus sits at an awkward place in the sequence. An ice giant that seems to behave like neither the gas giants nor like Neptune, its supposed twin. It's an outlier, an anomaly, something that doesn't fit the pattern. The atmospheric composition differences matter and are well understood. Uranus has more methane than Jupiter or Saturn, and methane absorbs red light while reflecting blue light, creating the distinctive blue-green color that makes Uranus recognizable even to casual observers. The methane also affects atmospheric chemistry in fundamental ways. influencing what compounds can form, what reactions can occur, how the atmosphere responds to heating and cooling. Jupiter's clouds are whiter and more complex because Jupiter has more ammonia and other compounds that form different colored cloud particles, creating bands and belts of different hues. Saturn's atmosphere is somewhere between Uranus and Jupiter, with a softer, more golden color, reflecting intermediate compositions and different chemical balances. But composition alone doesn't explain Uranus's featureless appearance, the bland and monotonous face that the planet presents to observers. If methane is the only difference, why does Jupiter look so dramatically more active? The low internal heat should matter, and it does. Without vigorous upwelling from the deep interior, without plumes of hot material carrying energy from the core toward the surface, the atmosphere remains more dormant, more quiescent. The winds are there, visible when you measure them carefully, but they don't produce the visible storm systems and cloud structures that dominate Jupiter's appearance and make it so visually striking. The Great Red Spot on Jupiter is a storm system that's been raging for at least 350 years, possibly much longer. Nothing like it appears on Uranus. The bands and zones on Jupiter are clearly visible, colored clouds in distinct patterns. Uranus shows almost none of this visible structure. The difference is striking and troubling to scientists trying to understand planetary atmospheres. The moons are another point of comparison that reveals differences. Jupiter has dozens of moons, some of them large, some of them geologically active, including the famous 4 Galilean moons that were among the first objects discovered through a telescope, besides the Sun and the Moon itself. Saturn has dozens as well, with Titan being a particularly remarkable world with a thick atmosphere and surface features suggesting a complex geology. Uranus has fewer large moons and no geologically active bodies that we know of. The smaller mass of Uranus means its gravity is weaker, so it captured fewer large objects during its formation. But this also means the moons it does have exist in a less crowded environment, less influenced by other bodies, following simpler orbital dynamics than the complicated gravitational dances that occur at Jupiter or Saturn. The rings are another comparison point that illuminates differences in planetary systems. Saturn's rings are famous, bright, obvious, dominating the planet's appearance even from casual observation, visible even through small telescopes. Jupiter's rings are faint and difficult to observe, known to exist but not spectacularly visible. Uranus's rings are even more elusive, dark, narrow, confined, requiring sophisticated telescopes and careful observation to detect at all. This likely reflects differences in their composition and origin. Saturn's rings contain abundant water ice, which reflects light effectively, bouncing sunlight back to space. Uranus's rings are darker, composed of older material, possibly contaminated with organic compounds that absorb light, making them difficult to observe. The differences in ring systems likely reflect different histories, different capture events, different mechanisms of ring formation and preservation. Understanding Uranus in comparative context reveals that it's not just a smaller version of Jupiter. It's a genuinely different type of planet, an ice giant following its own rules, playing by physics that we don't yet fully understand, obeying laws that we haven't yet deciphered. The formation of Uranus stretches back to the beginning of our solar system, to a time about 4.5 billion years ago, when the solar system didn't exist yet, when there was no clear distinction between planets and empty space. There was only a massive cloud of gas and dust, slowly collapsing under its own gravity, contracting inward from the immense cold of interstellar space. As the cloud collapsed, it rotated faster and faster due to conservation of angular momentum, spinning into a disk, a flat plane of material rotating around the center. The Sun formed at the center of this disk from the densest, most massive portions of the collapsing cloud. Around it, smaller objects began coalescing from the dust, tiny grains sticking together through electrostatic forces and simple gravity. Those grains accumulated into larger objects, pebbles becoming rocks, rocks becoming boulders. These objects collided and merged, forming even larger bodies, growing progressively larger and more massive. This process, called accretion, continued for millions of years, building up the planets from tiny starting seeds, from dust specks to planetary-sized worlds. The inner solar system formed first, where the Sun's heat was intense enough to vaporize volatile materials like water, ammonia, and methane. Only rocky and metallic materials could remain solid, so the inner planets became small, rocky bodies, the terrestrial planets we know as Mercury, Venus, Earth, and Mars. The outer solar system was colder, far enough from the Sun that the solar wind and radiation couldn't blow away the gases. Volatiles could remain solid there, allowing larger objects to form, allowing ice and rock to accumulate into massive bodies. Jupiter formed first, somewhere around where it orbits today, though its exact formation location is debated among scientists and remains a subject of ongoing research. Saturn formed next, slightly farther out, following similar growth mechanisms. These gas giants rapidly accumulated hydrogen and helium from the primordial solar nebula, growing to enormous sizes before the nebula dispersed, before the solar wind swept away the remaining gases. Uranus and Neptune formed later, when the nebula was thinner and accretion rates were lower, when fewer particles were available to stick to growing planetary cores. They grew more slowly than Jupiter and Saturn, accumulating less hydrogen and helium, remaining as ice giants rather than becoming gas giants. The transition between ice giants and gas giants was determined by when, in the solar system's history, each planet reached sufficient mass to capture the remaining nebula gases. Jupiter grew large enough early to grab a massive atmosphere. Neptune grew large enough later, when less gas remained. Uranus ended up somewhere in between, with an intermediate amount of hydrogen and helium, with an intermediate atmosphere compared to the true gas giants. But the actual formation timeline and location of Uranus is contested among planetary scientists, with evidence pointing in different directions and models remaining uncertain. One model, the Standard Model of Planetary Formation, suggests that Uranus formed roughly where it orbits today, at about 19 astronomical units from the Sun, building up its mass gradually from dust and debris in that region. Another model, the Grand-Tack hypothesis, suggests that Uranus formed closer to the Sun and then migrated outward as the solar system's architecture changed, as gravitational interactions between planets moved them from their original orbits. This is where the giant collision comes into the story, and where the tilt of Uranus becomes relevant to understanding its formation history in a broader context. If Uranus was struck by a massive protoplanet early in its history, this impact could have tilted the planet, knocked it off its original axis, and possibly scattered it to a different orbit, changing its entire trajectory through space. The collision would have been catastrophic, releasing enormous amounts of energy, creating a cataclysmic event that fundamentally altered the planet's properties. The impactor, an Earth-sized or larger body, would have struck Uranus at an oblique angle, transferring tremendous momentum, changing the planet's rotation axis, altering its spin in a dramatic way. This collision might have occurred relatively early in the solar system's history, within the first 100 million years or so, during the chaotic era when planets were still settling into their final orbits. The timing matters because it affects how much energy was left in Uranus after the impact, how much heat from the collision remained trapped inside the planet. If the collision happened early, when the Sun's radiation hadn't yet dissipated the primordial nebula, the impact energy might have been distributed more readily. scattered by remaining gases and particles. If it happened later, the energy would have been trapped within the planet, heating it for billions of years afterward, providing a heat source that would sustain the planet into the present day. This heating would explain why Uranus should have more internal heat than it does. But Uranus doesn't have more internal heat. It has less. This is where the mystery deepens, where the straightforward explanation breaks down. Some scientists have speculated that the collision that tilted Uranus also fundamentally altered its internal structure in ways that prevent heat from escaping, that trap heat deep inside or allow it to dissipate rapidly. Maybe the impact mixed the interior thoroughly, destroying the layered structure that normally allows convection and heat transport, creating a homogeneous interior that can't circulate effectively. Maybe it created a barrier in the upper atmosphere or mantle that insulates the core, preventing heat from flowing outward into space. Maybe the collision was so violent that it ejected material from Uranus, reducing the planet's total heat content, blowing away material that would have contained thermal energy. Or maybe Uranus simply cooled faster than Neptune for reasons we don't yet understand, through some process that operates more efficiently on Uranus than on its neighbour. The formation of Uranus's moons is also contested, with some moons possibly forming from Uranus's circumplanetary disk at the same time the planet formed, accreting from dust and debris circling the planet. Other moons might be captured objects acquired later, asteroids or planetesimals that wandered too close and were captured by Uranus's gravity. The rings might have originated from a shattered moon, destroyed by some collision or tidal interaction. Or they might have formed from material in orbit around Uranus at the time of its formation, primordial rings created during the planet's early history. Or they might be captured comets and asteroids, material from the outer solar system that ended up orbiting Uranus. The magnetosphere's origin is equally mysterious and equally contested. Magnetic fields on planets are thought to be generated by convection in electrically conducting layers in the interior, usually in the liquid outer core or in a mantle that's sufficiently hot and dense that it behaves like a fluid, capable of movement and circulation. On Uranus, the location where the magnetic field is generated remains unknown, uncertain, a matter of debate among researchers. The offset and tilted magnetic field suggests that whatever is generating it is not at the geometric center of the planet, not aligned with the axis of rotation. The field might be generated in a thin shell deeper inside the planet, off to one side, away from the center. Or it might be generated by some other mechanism we don't fully understand. Some process unique to Uranus that doesn't operate on their planets. The formation and evolution of the magnetosphere over billions of years probably involved changes in the planet's internal structure, cooling and solidification of regions that were once liquid, circulation patterns in the interior shifting as the planet aged and cooled. All of these processes left fingerprints on the magnetosphere, creating the unusual configuration we observe today, a relic of Uranus's complex history. When William Herschel discovered Uranus on March 13th, 1781, he didn't immediately know what he'd found, didn't understand that he was looking at a planet, that he was witnessing the expansion of human knowledge. The object he observed through his telescope looked slightly extended, not quite point-like like a star should appear. It had a disk of some sort, a measurable size, suggesting it wasn't a distant star, wasn't infinitely far away. Herschel initially thought it might be a comet. That was a reasonable hypothesis at the time, a sensible first interpretation. Comets were relatively frequently discovered, appearing as new objects in the night sky several times per year. Their appearance through a telescope could sometimes resemble this object, show a similar extended appearance. But observations over following nights revealed something unusual, something that didn't match the comet hypothesis. The object wasn't moving the way comets move, wasn't traveling across the sky rapidly. Comets have rapid proper motion across the sky as they travel on their elliptical orbits, coming close to the sun and then receding back into space, returning to the cold of the outer solar system. This object was moving very slowly, almost imperceptibly, barely advancing from night to night. Its orbit was nearly circular, not the elongated ellipse typical of comets. Its motion was consistent with something orbiting the sun at an enormous distance, taking many years to complete a full orbit, a true planet rather than a temporary visitor. This suggested a planet, not a comet, a fundamental addition to the known solar system. Other astronomers confirmed the discovery, observing it independently, verifying Herschel's findings. Within weeks, it became clear that a new planet had been found, the first planet discovered in recorded history, the first addition to the known solar system in 2,000 years. It was a moment of profound significance for humanity. It shattered the assumption that the solar system was known, that humans had already discovered all the planets, that the solar system was a fixed and unchanging arrangement. It revealed that there was more to discover, that the solar system was larger and more complex than anyone had imagined, that expansion and discovery were still possible. The naming of the planet became a matter of some dispute among the scientific community, with different camps arguing for different options. Herschel wanted to name it Georgium Sidus, after King George III of England, after the reigning monarch who represented the nation of his birth and patronage. This was not an unusual practice at the time. Planets were named after classical gods, and new discoveries were sometimes named after monarchs or other notable figures, especially if the discoverer was trying to gain favor or support from those in power. But other astronomers objected strenuously to this suggestion. They argued that planetary names should follow the convention of classical mythology, that Georgium Sidus broke with tradition, that it violated the established pattern of naming planets after Roman gods. Johann Bode suggested the name Uranus after the Greek god of the sky to maintain consistency with the other planets. Jupiter, Saturn, Venus, Mercury, Mars, all were named after classical deities. Uranus fit perfectly into this existing system, maintaining the pattern, preserving tradition. The name Uranus was eventually accepted, though not without some objection from those who supported Herschel's proposal. The planet's name reflects a cultural moment, a decision to maintain classical conventions even when naming newly discovered worlds, a choice to prioritize consistency and tradition over contemporary politics. It reveals something about the scientific community of the time, its commitment to consistency, to tradition, to maintaining a unified system of nomenclature even as the solar system grew and expanded. Uranus became part of mythology, incorporated into the classical pantheon, given a place in the traditional ordering of the cosmos. In popular culture, Uranus has been referenced countless times, sometimes respectfully in serious scientific contexts, sometimes with humor and sexual innuendo because of unfortunate linguistic coincidences in English. The planet's name has proven remarkably resilient, surviving centuries of cultural change, technological advancement, shifting scientific understanding. It remains the official name, recognized internationally, used by astronomers and casual observers alike. The discovery of Uranus had profound implications for astronomy and for humanity's understanding of the cosmos. It demonstrated that the solar system could still surprise observers, that discovery and investigation were still possible even in the late 18th century, that exploration was far from over. It inspired searches for more planets, motivated astronomers to look even farther into the solar system. Specifically, irregularities in Uranus's orbit suggested the presence of another planet farther out, perturbing Uranus's path through space, causing its orbit to deviate slightly from perfect predictions. This prediction led to the discovery of Neptune in 1846, confirming that the pattern of planetary discovery continued. The existence of Uranus also supported the nebula hypothesis, the idea that the solar system formed from a collapsing cloud of gas and dust. If small, distant planets could form at Uranus's distance from the Sun, then the solar system must have had a period of formation when conditions allowed bodies to coalesce across its entire extent, across all the distances from the Sun out to and beyond Uranus. The discovery fundamentally changed humanity's place in the cosmos. We were no longer residents of a solar system with a known and fixed extent. We were inhabitants of a solar system that could still yield discoveries, that stretched farther than we knew, that contained worlds we hadn't yet found. The observation of Uranus has always been challenging, difficult in ways that ground-based observers initially didn't fully appreciate. The planet is dim, receiving so little sunlight that ground-based telescopes struggle to gather enough photons to produce clear images. Imagine trying to photograph something billions of miles away that's barely reflecting any light, and you get a sense of the observational challenge. Throughout the 19th and 20th centuries, telescopic observations improved gradually as technology advanced. But Uranus remained a pale, featureless disk, difficult to study in detail, refusing to reveal its secrets to patient observers. The invention of photography allowed observers to record images of Uranus permanently, creating permanent records that could be analysed and compared, allowing researchers to track changes over years and decades. Later, spectroscopy revealed the planet's composition, showing the absorption features created by methane and other atmospheric compounds, telling us what the planet is made of without ever touching it. Radio observations in the 20th century provided new data about the planet's magnetosphere and thermal emissions, new windows into understanding the planet's properties. But all of these observations were limited by distance, by the fundamental constraint that Uranus is nearly 2 billion miles away, farther than most people can meaningfully conceptualize. Light from the Sun bounces off the planet and travels back to Earth, carrying information about the planet's surface and atmosphere. But the amount of light is small, diminished by the vast distance, reduced to a trickle compared to the bright light reflected by Jupiter or Saturn. The planet appears tiny even through powerful telescopes, a small disk rather than a detailed world. Resolving details, seeing surface features or atmospheric structures remains extraordinarily difficult, probably impossible with current Earth-based technology. The Hubble Space Telescope could identify some features, subtle variations in brightness and color, small-scale differences in the planet's appearance. But these observations don't match the detailed views available for Jupiter or Saturn, don't provide the clarity that scientists want. The James Webb Space Telescope can observe Uranus in infrared wavelengths, detecting heat radiation rather than reflected light, providing better views of the upper atmosphere. But even Webb is limited by distance, by fundamental physics, and by the need to observe through Earth's atmosphere, which distorts light and interferes with observations, creating a barrier between us and the distant world. Recent observations using advanced telescopes have revealed some surprising details about Uranus that weren't anticipated by scientists working from older data. The upper atmosphere is cooling, as mentioned earlier, a trend that remains unexplained by current understanding, a mystery that challenges our theories. Occasional storm systems have been detected, small weather features that develop and dissipate on timescales of days or weeks, proving that Uranus isn't as dormant as it appears from a distance. The auroras shift and evolve in patterns influenced by the tilted magnetic field, creating displays of light that form in unexpected locations, surprising researchers who study atmospheric phenomena. The moons continue to yield surprises, continue to reveal new secrets, with new discoveries made using advanced detection techniques that push the boundaries of what's observable. The rings remain enigmatic, their composition and origin still debated among scientists, their dark material still mysterious. The most recent discoveries have come from the James Webb Space Telescope, which can detect faint objects and measure properties that would be invisible to previous instruments, which can see things that earlier telescopes simply couldn't reach. The discovery of new moons has accelerated in recent years as detection technology has improved dramatically, as instruments have become more sophisticated and powerful. Where older telescopes could only find the largest, brightest moons, the ones that were obvious and easy to detect, modern instruments can detect objects a few kilometers across, tiny worlds previously hidden from human knowledge, satellites we didn't know existed. The complete picture of the Uranian system remains incomplete, fragmented, partial. Many questions about the planet, its formation, its internal structure, its magnetosphere, and its system of moons await answers that probably will only come when a dedicated spacecraft returns to investigate the planet directly, when a mission commits to studying Uranus with the attention it deserves. That future mission remains planned but uncertain, remains subject to budgetary decisions and political priorities, remains contingent on whether society decides to commit resources. But the scientific case is clear, unambiguous, compelling. Uranus deserves investigation. It deserves a mission that treats it as a priority, not as an afterthought to exploration of other worlds, not as something to study when we've exhausted other options. When you step back and consider everything we know about Uranus and everything we don't know, you're left with a profound sense of how much mystery remains in our own cosmic neighborhood, in the region of space that should be most familiar to us. This is a planet orbiting our Sun, a member of our solar system, part of the same formation event that created all the planets, born from the same collapsing cloud of dust and gas. And yet, we understand it only incompletely, know only its most basic characteristics, have visited it only once, briefly, more than 30 years ago, capturing a few hours of data that we're still analyzing. The extreme axial tilt remains a defining feature, a reminder that planetary formation is complicated, that collisions happen, that cosmic chaos shaped our solar system's architecture, that violence and disruption are woven into the fabric of planetary formation. The low internal heat remains a puzzle, something that doesn't fit our models, something that forces us to question our assumptions about how planets work, that reveals gaps in our understanding. The featureless appearance conceals extreme winds and complex dynamics that we're only beginning to understand, that reveal themselves through careful measurement and analysis. The magnetosphere is bizarre, tilted and offset in ways that have no parallel elsewhere, no equivalent example in our solar system, standing alone in its unusual configuration. The moons are geologically diverse yet poorly understood, their histories obscure, their current conditions only partially known. The rings are dark and mysterious, their composition uncertain, their origin debated, their future evolution unknown. The atmosphere is largely unknown, with composition and chemistry that remain incompletely characterized despite decades of observation. The planet sits at a distance that makes casual observation impossible, that requires powerful telescopes and sophisticated analysis, that keeps it at the edge of what we can easily investigate. And yet, despite all these challenges, despite the distance and the difficulty and the incomplete knowledge, Uranus remains scientifically compelling, remains worth serious attention and investigation. It offers windows into planetary physics that we don't have elsewhere, that provide unique perspectives unavailable from any other world. It challenges our models, forces them to confront observations that don't fit, that reveal fundamental gaps in understanding. It forces us to think harder about how planets form, how they evolve, how they interact with their environment, how the physics we think we understand actually operates in the real universe. Understanding Uranus means understanding a category of worlds that dominates exoplanetary discoveries, that comprises a significant fraction of planets around other stars, that appears more frequently in distant systems than Jupiter-like gas giants. If we ever encounter life on other worlds, if we ever discover civilizations orbiting distant stars, many of those worlds will be ice giants similar to Uranus, making understanding our local example crucially important. Understanding Uranus, understanding how ice giants work, how they develop atmospheres, how they maintain magnetospheres, how they support moons, all of this knowledge will prove invaluable, will inform our understanding of worlds we'll encounter in the future. But beyond the practical scientific case, there's something more fundamental. Something that motivates scientists beyond rational calculation and abstract knowledge. Uranus represents a frontier, a world that remains partially unknown, that still holds mysteries, that still has the capacity to surprise us, to teach us something new about how the universe works. In an era when much of the solar system has been mapped and explored, when our planet has been catalogued and analysed in tremendous detail, when even distant moons have been visited by spacecraft, there remains this one distant world that sits at the edge of our knowledge, still mostly mysterious, still waiting for closer investigation. The mystery of Uranus is the mystery of discovery itself, the reminder that even in our own cosmic backyard, wonders remain, that exploration is far from finished, that surprises still await. The planet continues to orbit, continues to rotate on its side, continues to maintain its strange and beautiful physics 4.5 billion years after its formation, continues to exist according to laws we don't fully understand. Perhaps one day a spacecraft will venture to that distant world, will enter orbit around it, will investigate its moons and its rings and its magnetosphere and its atmosphere with the detail and precision that Uranus deserves. Perhaps in that future, we'll finally understand why the planet is tilted, why it's so cool inside, why its magnetic field is offset and tilted, why its atmosphere appears so featureless yet contains such violent winds. Until that day comes, the mysteries persist, the questions remain unanswered, and Uranus holds its secrets beneath the blue-green clouds and the extreme seasons and the tilted magnetic field. The planet endures, waiting, unknowable, except for the fragments of information that we've managed to gather from billions of kilometers away, incomplete impressions assembled from distant observations. And that's perhaps the final mystery of Uranus, the biggest one of all, the question that motivates future exploration. What would we discover if we finally went there? If we finally committed the resources and the time and the effort to returning to this strange and distant world? What secrets would be revealed? What new mysteries would be uncovered? What would Uranus teach us about planetary physics, about how the universe works, about our place in the cosmos? We don't know. Not yet. And that uncertainty, that possibility, that sense of unfinished exploration, that awareness that discovery awaits, is perhaps the most compelling reason to return.